So let us start with quantum electrodynamics. So as I've already mentioned to you previous lectures that interaction Lagrangian density for EV is of the following form. Where capital Q is -1. So I have this for the charge with electron I have taken can be either minus or plus. A positron also. So I have taken this to be mod of E. Whatever sign E is, it will be always plus. And for I have put in a fact extra factor of Q, which takes into account whether it is an electron or a positron. For an electron, Q is equal to -1. And this I there. So this is the interaction Lagrangian density minus Q multiplied by AB. And the Hamiltonian density minus I, that is Q. So what we shall, so this is basically the Lagrangian density, and therefore you can immediately see what the vertex is. The vertex will be something like this. Immediately write down the factor for the final rule for the vertex is minus I or this is the vertex. Final rule for the vertex. So at this point. So what we shall first do today is we shall look at Rutherford scattering in the non-relativistic limit. If you remember that Rutherford discovered this scattering of alpha particles from the nucleus of an atom. It was in the early 20th century or just late early 21st century or late 20th century. And at that time, there was no quantum electrodynamics. That is the point that should be clear. So Rutherford discovered this phenomena of scattering of alpha particles from the nucleus of an atom, and he calculated the cross section for that process, and it was named as Rutherford scattering cross section or Rutherford scattering. And it established what it did was it convincingly established the nuclear structure of the atom. So it established that indeed there is a nucleus inside that. That was the conclusion which was drawn from Rutherford scattering experiment, and he calculated the scattering cross section. But at that time there was no quantum electrodynamics. This is the point that should be clear. So what we are studying today is we are trying to study the scattering of an electron from a very heavy positively charged nucleus of an atom. So we are looking at scattering of an electron from a heavy charged nucleus of an atom. And this is also an example of Rutherford scattering. And you can go ahead and calculate the cross section for this process. But you can do it by using techniques which do not use any theoretical tools or which does not use the Feynman rules. So these cross sections were actually derived at a time when quantum electrodynamics was not there, and there were no Feynman rules and quantum electrodynamics, but these cross sections were derived. But the advantage of quantum electrodynamics, of using quantum electrodynamics, you can say that this is a byproduct of quantum electrodynamics. That once you have the Feynman rules in your hand, the calculation of this cross section becomes much simpler. So what we shall do in these lectures is that calculate the cross sections of this process by using the rules or by using the Feynman rules. We already know the Feynman rules. For this example, the Rutherford scattering of an electron, we shall explicitly calculate everything without using the Feynman rules, and then we shall also see how we could have got the answer in just a moment, in just 1 second by using the Feynman rules. And for the other processes, we shall straight away use the Feynman rules. So this is our plan. So here you see that an electron is coming and it is getting scattered, and here there is a positively charged nucleus. That I denote it as a field mu, classical. See here, you should remember that since the nucleus is very heavy and it is not moving, it is only the electron that is scattered. We shall assume that the electron is getting scattered due to a classical potential it sees because of this positively charged nucleus. So in a sense, this potential that the electron is seeing, or electron is getting scattered in this potential, is not this electromagnetic potential is not dynamical in nature, it is static. Therefore, just put in a symbol like this to show that there is something sitting over here and it produces a static electromagnetic potential. That potential is given by this in the momentum space. How do you get Q? We will come in a moment. So this static electromagnetic potential, you can actually write it the following way. The zeroth component basically. So this, let us suppose that this nucleus has atomic number Z. This will be Z mod E, 4 pi. This and
So what does the subscript of A means A0? Is it chlorine?
this is classical. Classical. You
Okay.
can just remove it. If it's confusing, you can remove it. What I am saying is that the electron is seeing a classical potential here, classical electromagnetic potential. Okay,
Okay, sir.
that is what I am saying. So this is zero. So the static positive electromagnetic potential is described by these two equations. Okay, and if you take a Fourier transform of this immediately tells you that A tilde 0 basically Z on E by, and that is what this is. So here actually you have the other component is 0, so just have 0. So this is the Feynman diagram that you have electrons coming and getting scattered in the classical potential of this, the static potential of this positively charged nucleus of the atom, and these are the electrons, and these are the components of the gauge. And therefore, now what we need to calculate is this is the in state, this state is the in state, this is the out state. This is the scattering angle. So this is what we need to calculate. And therefore, know that this can be written as sine S. This. And now this part is time ordered product. We shall say H1 to be equal to 1. So we worry about that. Then you have hi. Hi is you can Q, Q is what? Q is minus 1 for an electron. This will be plus the body. Over here, this is the body. And then you have psi bar and Q. This we can write it down as prime time order product 1 like module here, model P. Plus dot. We shall only calculate this at the first order in perturbation theory. So you have only this diagram at the tree level. There are no loops. So we have the process. Huh? This one plus I. So we have plus I, and then you could have kept Q here, Q and body, and then it is up to you to put in what the value of Q is. But for electron, I'm setting Q is equal to minus 1. The first term is this. This will obviously not contribute to the scattering or the probability of scattering. This will not contribute because nothing happens here. So this is not interesting. The only interesting term is this one. We have I. Go next. Time order product of psi bar. See, this is not an operator because this is a classical potential. Now you can realize the difference. What I can do is I can just put it outside. This is not an operator. Had this been an operator, then you see you are in trouble because there is only one particle here, one particle here. So two particles, there are three operators. So it will be 0. So it will annihilate. So there are more number of operators than the number of particles. So even if you apply mixed contract and you need the two size, then also one operator will remain and it will kill the metal. So this is not an operator, this is a classical potential. So let us just look at this term. So this term I write it down as A1, that is equal to I. Here also there will be a module of E before X. Then write this A2 X here. And then E prime, you can write it down as vacuum A and S. So E prime we are writing like this, R0, A E prime S, S prime. So this electron has momentum E S, this electron has scattered electron also has momentum time. Then we have psi bar X V I X, and this P you can write it down as a dagger actually what you can do is you need to just put it as prime. Prime is prime. Let me show what I've done. I'm just calling this state as P prime S prime. That's PS. That is what I've done. So if this is okay, then you can write this PS state as A dagger P comma S state 0. Okay. And now we have to calculate this thing. It is easy to calculate that this contraction and this contraction. Nothing more. So that will give us I. So these are the two contractions that are important here. So this contraction, you know how to calculate this contraction. This contraction is basically give us x. This will give us q bar s prime prime for I and x. Then we have and this contraction was this because you can see that psi you have A. So A and A dagger will give you an trivial contribution and psi bar this you must have you have two terms, you have A dagger and B, but it's only A dagger which will contribute A. So that will give you a non-trivial contribution. Other term will be 0. So from this one we will have 2s B to the power of minus I. That is what we should do. Now, this mu and gamma mu you can sum. Therefore, this will become gamma 0, A 0, and the other term is 0 because A vector is 0. AI component, the I components are 0. Therefore, we have integral before x. This will give us q bar s prime and gamma 0. A0 is there for D by. So here we have to be careful. To be careful. What I shall do is let this be non-use with this will be e to the power of I prime x. Now, what I shall do is I shall Fourier transform this. This will be d4 by 2 pi over 4 a tilde function of k e to the power of I. Okay. Now you can do the sum because once again the AI component of k's are also 0. Now you perform the sum over mu. This becomes gamma 0, this also becomes gamma 0. But A tilde function of k, that is basically this is there. So this is what we have, and this e to the power of I k dot x, and just lump it. Okay, is it okay?
Yes, sir.
Good. So now you can see that we write it over here. So this is I mod of P, then integral before A by 5 4 Z. Okay, you can this you can write as Z E square. No mod is required now because there are two E's now. So this becomes Z E square before A by 2 pi over to the power of 4, and then we have U bar S prime gamma 0 U is, and then we have the integration over x. So x, we also have this k vector square. This is I prime. And now we can perform the integration over x is 2 pi to the power 4 times the four-dimensional Dirac function prime minus k. So this 2 pi 4 by to the power 4 is cancels. You can now see that this is the overall energy momentum conservation kind of thing, because you have P coming in, P prime going out. So this should be P. So if you call this K, then we have P plus K minus P prime is equal to 0. And therefore K is basically P prime minus P. So that is what you get from here. So just do the K integration. To perform the K integration, then you get Z square U bar S prime prime comma 0 to S P. And there is a K square here, so you can replace this by mod of P prime minus P. So this is your end result for this amplitude K1. I missed an I think. There will be an I here. There's an I over there. So A1 will be I times this. So what will it be? And which one? B4K. B4K is a Dirac function. So you replace K by P minus P, P prime minus P, this K vector square. So that gives you this factor in the denominator. So what we have ultimately got is the following. This the scattering amplitude, the probability scattering amplitude. This is A1, this is denoted by A1, and this is equal to IZ P square by this factor in the denominator, P bar S P prime comma 0 to S P. And now, in order to calculate the probability of this scattering, you just need to take a mod and square it up. Take mod of this and square it. So mod square gives you the probability of scattering. But today, what we shall do, we shall take a non-relativistic limit of this. So if you take a non-relativistic limit of this, I just leave it as an exercise for you to complete. With the non-relativistic limit, this U bar is prime. So in the what happens physically, what happens in the non-relativistic limit is that you don't care about the spin of the particles, right? And therefore, this factor that you have here becomes twice of m, twice of mass of the electron. This is what we get. Therefore, this would imply that A1 nothing but I z square by p prime p square times twice of p. So this is the result of the scattering amplitude at the tree level. So we are
Sir,
only at the tree level. Yes.
uh, for
Yes.
that non-relativistic limit, how are we getting to M?
That I leave it to you as an exercise. Please find it
Okay,
out. Because
okay, sir.
you already have some, you have already taken a course in Dirac equation.
Okay, sir. Okay,
So
sir.
I can give you a hint. So you can basically write UP as UP. So if I give you the hint, then there is nothing more to do. Something like this. Okay. So if you take this and just compute, you know what the form of gamma zero is. Since UP is this, therefore you know what U bar is. So U bar is what? U this is the Dirac adjoint. So this is U bar. U bar is U dagger gamma zero. Gamma zero square is identity. So this full thing is nothing but U dagger U. And U is this. So you just compute, take dagger of that and then compute U dagger U, you will get twice of it. So this gives you a factor of 2m over here. So therefore the amplitude A1 becomes this. And now there is nothing more to do. What you can do is I will just switch here. I hope you can see this part of the board. So let's take a mod square of this full
Can you
thing.
just zoom in, sir? Yeah.
Yes, I will zoom in. So if you take a mod square of this, then what you will get is the following. It will give us z square to the power 4, 4 m square divided by this t minus t prime whole square. But this t prime minus t prime you can understand in this way. We have d over here, and then it is getting scattered times angle is theta. So for elastic scattering, so you can write t minus t prime mod square as t prime minus t as t prime square plus t square minus twice of t prime dot t, right? For elastic scattering, t prime is basically p equal to p mod of p. Therefore, this gives us, this will give you 2 of p vector square, and this is basically the angle between p and p prime, the angle is theta. So it was 1 minus cosine of theta. So that is 4 p vector square sine square. So that is what p prime minus p mod square is. So if twice, it gives you 4. Let's write it over here. Okay, you should just remember that you have taken a mod square. So this will be z square e to the power of 4, 4m square, and this will be to the power of 4. Right? But square is 4p square this. So to the power of 4 means 16 p4. From now on, I am just calling this as p. So this is not 4 momentum. This is the magnitude of this p vector. So this becomes p to the power of 4 sine to the power of 4 double. The theta is the angle of scattering. So this is the result that you get. And in terms of velocity, so this mass into velocity. This V is also again the modulus of the velocity vector. So this plus 4 z square or 4 m square by 60 m4 d4 sine 4 by 2. M square and m square cancels, so this gives you 2. So it is 4z square to the power of 4 by 16 m square d4 sine 4 to the sine 4 theta by 2. That is the mod square of A1. Okay. This is what we get from here. Now there is a very important concept of scattering cross section. It is basically, I will tell you what do I mean by scattering cross section. The concept is quite simple. Suppose you have some hard sphere and its radius is small a, and it is in an area capital A. Okay, so what I am saying is this: you have some area A, and here you have some sphere. Radius is small a, so this area is pi a square. Okay, and suppose you are throwing some sphere from outside. What is the probability that that particular sphere that you are throwing from outside will hit this sphere? What is the probability? Probability would be of this scattering event very simple to calculate. It's pi a square by capital A, right? And therefore, pi a square is nothing but Ps into A. Scattering cross section. These are for classical particles, but you can just take it over to quantum mechanical scattering also. This pi a square is basically the cross section, the area of cross section that this target particle. This is the target particle. This pi a square is basically the area of cross section that this target particle shows to the beam that is coming, and therefore this in the literature is said to be the cross section. So this is basically roughly the concept of cross section, but I shall again discuss it in details in another lecture. But for now, you just remember that this is what you mean by cross section. In this case, the scattering cross section is given by the following result. Once you have this, scattering cross section is denoted, the differential scattering cross section is denoted by this sigma d omega, and that is basically this A1 square mod square by 4 pi whole square. So this sigma d omega is A this mod square, amplitude mod square by 4 pi whole square. You know what A1 mod square is? This is this particular thing, and therefore this sigma d omega you can calculate immediately. You can finish the calculation. If you do it over here, sigma omega is, you have a 4 pi whole square downstairs. So it is 4 square by this. You can also see from here that this 4 will cancel with 16 and it will be a 4 downstairs. Therefore, what you have is, you have a z square, then you have a t square by 4 pi whole square. This 4 pi comes because we divide by 4 pi whole square. This gives you e to the power of 4. Therefore, you have z square, t square by 4 pi whole square. Then divided by, you have 4, the denominator, you have n square, e to the power of 4, sine to the power of 4. And this E square by 4 pi is nothing but the fine structure constant. Therefore, you have Z square alpha square by 4 square. So this shows that the result depends on the strength of the coupling, the coupling strength that is precisely the fine structure constant that appears in the case of electrodynamics, and that is E square by 4 pi. Alpha is E square by 4 pi, and therefore the final result for the differential cross section is Z square alpha square divided by 4 m square V4 sine to the power of 4 theta by 2. And this precisely, if you remember your classical mechanics course or quantum mechanics course when you studied Born approximation, scattering theory in quantum mechanics, you precisely remember that the cross section, the Rutherford scattering cross section formula is precisely this. You get everything, you get the dependence, the sign dependence, the short power of sign, the scattering angle dependence coming to the sign B. Then you have the atomic number dependence coming to Z, mass of the electron, velocity of the electron, and the fine structure constant. So this is the Rutherford scattering cross-section formula that we have now derived by using quantum electrodynamics. And you can immediately see that it is very easy to calculate A1. So if you look at the formula for A1, so A1 was this. This was A1, right? This was A1. This was A1. And this was the final result for A1. And you can immediately see that you can write down the final result for A1 very easily, because what you need to do is just put in the appropriate factors. There is one vertex here, and just put in the final rules. So the final rules for the vertex you already know, and this Z, the extra Z factor, comes from the classical potential that the electron sees due to the positively charged nucleus. Positively charged nucleus produces a classical potential, and that potential is precisely in the Fourier space, in the momentum space. It is basically Z mod E divided by this momentum. So it is this momentum K, and this momentum K is basically the difference between these two momentum. That is the classical potential, as seen by the electron. So you put in the final rule for the classical potential, then you have this external factor Q bar S prime E prime, and since there is only the zero
Can you change the board, sir, please?
sorry.
Can you change the board?
Okay, okay. We are okay. Now you can see the full board, right?
Yes, sir.
So let me just zoom it better. So you can see that you can immediately get this result A1, this result by using the Feynman rules. Just put in U bar S prime, E prime. Then for the vertex you will have a minus I E gamma mu, which is I E gamma mu, but mu you can sum, and there is a classical potential A tilde mu q, but A tilde mu q only the zeroth component is non-zero. So when you perform the sum over mu, you will only get gamma 0 over q. And then for the incoming particle you have USP, that is also taken care of. You have put in the vertex, and for this thing, for the classical potential, you have Z mod E by K square, which is this momentum, right? And that this momentum is what? This momentum is basically the difference of the three momentums of the outgoing electron and the incoming electron. So at one shot, without doing all these calculations, you could have written down what the scattering amplitude is by just writing down by just using the Feynman rules that you already know. And the Feynman rules will immediately give you this result. And then you just square it up, you will get the probability of scattering, and then you can calculate straight away calculate the scattering cross section by dividing by 4 pi whole square. And that would ultimately lead you to the Rutherford scattering cross section formula. This is precisely the Rutherford scattering cross-section formula. So let us stop here. I'm not sure whether Wednesday is a holiday or not. Wednesday is a holiday. So if Wednesday is not a holiday, then we shall meet on Wednesday. But Thursday is a holiday. So it is the Bengali New Year. So there will be no class on Thursday. But Wednesday, if there is no holiday, there will be a class. So let us stop here for today.